Hello, students, and a very warm welcome. Today, we're going to dive into a very important topic from the chapter Structure of the Atom. We'll be learning all about electronic configuration and valency. So, let's get started. Okay, so let's think about this for a second. We all know an atom has a nucleus right in the center, and then there are electrons somewhere around it. But are they just floating around randomly, or is there some kind of system to it? How do we know exactly where these electrons live? Well, that is the big question we are going to answer today. To answer that question, we first need to quickly go back and recall the work of the scientist Niels Bohr. You see, his model of the atom gives us the foundation, the starting point, for understanding where all the electrons are placed. What Bohr suggested was actually quite brilliant in its simplicity. He said that electrons move around the nucleus in fixed, circular paths. He called these paths orbits, or more commonly, shells. Each of these shells is at a set distance from the nucleus and has a fixed amount of energy. They're named, starting from the one closest to the nucleus, as the K shell, then the L shell, M shell, N shell, and so on. So, if these shells are like the houses where electrons live, how do we decide which electron goes into which house? Well, you can't just place them anywhere you like. There are specific rules for this arrangement. And this systematic way of arranging electrons into the different shells is exactly what we call electronic configuration. Now, the rules for filling up these shells were given by Bohr and Bury. There are three simple rules we need to get really good at. First, there's a rule to figure out the maximum number of electrons any shell can hold. Second, there's a special rule just for the outermost shell, and we'll see why that's so important later. And third, there's a rule about the order you have to fill them in. Let's take a look at each one, step by step. All right, let's break down that first and most important rule. The maximum number of electrons that can possibly fit into any given shell is decided by a very simple formula, 2n squared. Here, the letter n just stands for the shell number. So let's actually use this formula, okay? For the very first shell, the K shell, n is equal to 1. So we calculate 2 times 1 squared, which is just 2. So the K shell can hold a maximum of 2 electrons. Simple. Now, for the second shell, the L shell, n is 2. So that's 2 times 2 squared, which is 2 times 4, which gives us 8. The L shell can hold a maximum of 8 electrons. And what about the third shell, the M shell, where n equals 3? Well, it'll be 2 times 3 squared, which is 2 times 9. That gives us 18 electrons. See? It's very simple. Okay, let's pause for a quick recap. Based on what we just calculated, what is the maximum number of electrons that the L shell can hold? If you said 8, you are absolutely right. Excellent. Now let's look at the third rule, which is all about the filling order. It's very straightforward. It says that the shells have to be filled in a step-by-step manner. Think of it like this. Imagine you're filling seats in a classroom. You have to fill the first row completely before anyone can start sitting in the second row, right? It's the same idea. The K shell must be completely full before a single electron can enter the L shell. Let's see this in action with a real example. Let's take sodium. A sodium atom has 11 electrons. So how do we arrange them? Well, the first 2 electrons go into the K shell. Okay, now the K shell is full. We still have 9 electrons left to place. So the next 8 electrons will go into the L shell. Now the L shell is also full. How many are left? Just 1. That one last electron will go into the next available shell, which is the M shell. So the electronic configuration of sodium is written as 2, 8, 1. Let's practice with 2 more. Take chlorine, which has 17 electrons. The K shell gets 2, the L shell gets 8, that's 10 electrons used up. The remaining 7 go into the M shell, so its configuration is 2, 8, 7. Now what about neon? It has 10 electrons. The K shell gets 2, the L shell gets the remaining 8, so its configuration is 2, 8. Now notice something very important here. For neon, its outermost shell, the L shell, is completely full. Keep that in mind. It's a very important clue for what's coming next. So, why does all of this matter? How does this connect to chemistry? Well, that brings us to our next section. Now that we know how to arrange electrons, we can finally understand why atoms react the way they do. And the whole secret lies in that outermost shell. You could say it's the most important part of the atom when it comes to chemical reactions. The electrons that are in this outermost shell, they get a special name. We call them the valence electrons. So, for our sodium atom with the configuration 2, 8, 1, the number of valence electrons is Simply 1. What about chlorine with configuration 2, 8, 7? How many valence electrons does it have? 7, that's right. Knowing about valence electrons directly leads us to another key idea, valency. Valency is, simply put, the combining capacity of an atom. It's all about how many bonds an atom can form, and this capacity is decided by the number of valence electrons it has. You see, an atom always wants to become stable, and to do that, it will either lose, gain, or share its valence electrons. The number of electrons it needs to move around to become stable, that number is its valency. So what does it really mean for an atom to be stable? Well, the ultimate goal for almost every atom is to have a completely filled outermost shell. Scientists notice that atoms with 8 electrons in their outermost shell are chemically, well, lazy. They are stable and they don't react. This tendency of atoms to want to achieve a set of 8 electrons in their valence shell is called the octet rule. Octet just means a group of 8. Let's compare two atoms to really see this. Look at chlorine on the left. It has 7 valence electrons, so it's just one short of that stable number 8. This makes it very, very reactive. It desperately wants to find one more electron to complete its set. Now look at neon on the right. We saw it has 8 valence electrons. Its outermost shell is full, it's stable, it's satisfied, and it's non-reactive. It has achieved its octet. Okay, now we get to the really practical part, the part that I know is very important for your exams. How to actually calculate the valency of an element just by knowing its electronic configuration. Luckily, there are 2 very simple rules to follow. Rule number 1, if the number of valence electrons is 1, 2, 3, or 4, then the valency is simply equal to that number. Why? Because it's much easier for the atom to just lose those few electrons. Rule number 2, if the number of valence electrons is 5, 6, or 7, it's now easier for the atom to gain electrons to complete its set of 8. In this case, the valency is calculated as 8 minus the number of valence electrons. Let's apply these rules to a few examples. Look at magnesium. It has 2 valence electrons. That fits rule 1. So it will lose 2 electrons, and its valency is 2. Now, oxygen. It has 6 valence electrons. This is more than 4, so we must use rule 2. It's easier to gain 2 electrons than to lose all 6, so its valency is 8 minus 6, which equals 2. And chlorine. It has 7 valence electrons. It will gain 1 electron, so its valency is 8 minus 7, which is 1. All right, I want you to pay very close attention here, because this is where many students make a mistake in the exam. For an element like oxygen, they see the 6 valence electrons, and they write the valency as 6. This is incorrect. Please remember, the number of valence electrons is 6, but the valency, its combining power, is 2. Why? Because it only needs to gain 2 electrons to complete its octet of 8. Please do not confuse these 2 numbers. Okay, we have covered a lot of important concepts today. So let's just quickly summarize the key points that you absolutely need to remember for your exams. First, remember that electrons are filled according to the Bohr-Bory rules. Next, don't forget that super useful formula, 2n squared, which tells you the maximum capacity of any shell. The most important idea is that the outermost shell is the star of the show. It's what determines how an atom reacts. This directly leads to valency, which is just the atom's combining power. And finally, the ultimate goal for almost every atom is to achieve that stable octet, those 8 electrons in its outer shell. Look, if you have truly understood these fundamental concepts, you have built a very strong foundation in chemistry. You are now ready to confidently handle any question on electronic configuration and valency that comes your way. Keep practicing these examples. All the best.